Welcome back. My name is Dr. Elvis Assom. I am a senior climatologist at Climalogic Inc., an adjunct professor in the Global Institute for Water Security, University of Saskatchewan, and an associate of the Climate Risk Institute. Today, we'll learn about climate models and good practice for the use of climate model outputs. This session is divided into three major parts. In part one, we will discuss what are climate models. In part two, we will highlight good practice for the usage of climate model projections. And in part three, we will discuss some of the limitations of climate modeling. There is a connection between historical observations and climate model output. Typically, to produce application-ready data will require historical observations, which will be used for correcting climate model output during the historical period, and then using those correction factors to correct future climate projections through bias correction to derive application-ready data sets. How do we understand the climate system and come about producing climate projections? To do this, we use what are called climate models. These are numerical models used to understand the future evolution of the climate system as well as to understand the climate system itself. These climate models separate the Earth's surface into three-dimensional grid cells. The results of processes modeled in each cell are passed to neighboring cells to model the exchange of matter and energy over time. Grid cell size determines the resolution of the model. The smaller the grid cell, the higher the level of detail that the model will produce. More detailed models will typically have more grid cells, while low detailed models will have bigger grid cell sizes. So models with smaller grid cell sizes for the same location, the same space, would typically require higher computing power. So high resolution models require higher computing power for the same domain. Climate model resolution has been increasing over time since the very first IPCC, that is the Intergovernmental Panel on Climate Change First Assessment Report. And over time, different Earth system processes have been represented in these models. So the evolution of climate models reflects the kind of processes, physical processes that these models represent. So in the 1800s, we were mostly looking at energy balance models, and in the 1990s and 2000s, we have atmosphere ocean general circulation models. And in the 2010s and that of those models which accompany the IPCC 2013 report, we look at Earth system models. So it is difficult to model the climate system, and with scientific advances and computing advances, a lot of progress has been made to improve our understanding and representation of Earth system processes in these climate models. Global climate models and numerical climate models, which are used to study climate change on a global scale. And as I said, the resolution has been increasing over time, but still this resolution is not good enough to really understand a changing climate at a local scale. So typically, to use these model outputs in climate risk assessments, we apply what is known as downscaling. So downscaling basically helps us to translate what the global climate model, the GCM, simulated at a very large scale and down to a very small scale. It could be a small region such as this, or a particular project site. Two main approaches are often adopted to do downscaling. We call that statistical downscaling, or we do dynamical downscaling using regional climate models to produce application-ready data at a local scale, such as a watershed or a point where infrastructure is to be assessed. Interestingly, all models are wrong, but bear with me, some are useful. And you can see, since the 1960s, climate modeling has been improving significantly, and with higher computing power, the number of models produced during each IPCC assessment have been increasing. And just in 2022, in February, when Working Group 2 of the IPCC publishes their report, we'll have greater insights on some of the impacts of climate change that we might expect in the future. And we look forward to looking at these impacts using a range of the models which have been produced by IPCC Working Group 1. And this report has been released and is available online. CMIP 6. So CMIP is the Coupled Model Intercomparison Project Phase 6. Introduces new scenarios called shared socio-economic pathways. And the IPCC Science Synthesis report based on this CMIP 6 is expected sometime next year. Part 2. Now we will look at good practice for the usage of climate model projections. Using climate projections must ensure that the climate data selected represents an appropriate range of possible future climates, is fit for purpose, contains the information you require, and is robust. Example key considerations you should note. Choosing climate models is one. Choosing emission scenarios is another. Choosing time periods is also as important. Climate projections, note that climate projections are derived from more than 40 CMIP 5 and CMIP 6 models. When conducting a risk assessment, it is recommended to carefully select models that represent the range of future scenarios. You can see the spread. So if you choose a model that is lying here, then you are choosing a cold model. If you choose a model that is lying right at the top, you're choosing a very warm model. If you choose something in the middle, then you are choosing kind of a moderately warm model. So it is important to consider a range of cold, moderately warm to very warm models in your risk assessment. Use many scenarios. Why? For the near term, that is before 2050s, there's almost no difference between the various CMIP 5 and CMIP 6 scenarios. But as you go towards the long term, the emission scenario can have a large influence on the potential results. The influence of scenarios becomes very evident. You can see the large spread between, say, RCP 2.6 and RCP 8.5. So as you go towards the end of the 21st century, the importance of emission scenarios is very, very evident. So use many scenarios when doing a climate risk assessment. One other important consideration when using climate projections is when we want to choose time periods from which to extract climate projection data sets. And remember that decisions made today will have consequences for many decades in the future about water infrastructure investments. So climate projections must be carefully selected to match the design life of a specific water infrastructure project. For example, if you are doing a climate risk assessment of an irrigation canal which has a design life of about 50 years from today. Typically, you go to your climate projections portal and select climate projection data sets 50 years into the future from today. So you are looking basically at the 2080s. That is the time window from which you select your climate projections. If you are looking at a design life of 50 years for this water irrigation canal, you should not in any way come and extract climate projections for the 2030s. That would be wrong. You should be focusing on the 2080s. When trying to derive application-ready data sets and generate climate change signals, it is important that climate projections should never be compared directly with observations. Always remember that climate models are slightly different or biased compared to true observations and never reproduce the observations perfectly. So, for example, if we are to derive a climate change signal for a project site for which we are to do an infrastructure assessment, do not say you do not come to say in the 2080s get a climate time series for climate projections. Take that time series and compare it with observations. Never do that. You will get a very high temperature change of about 6 degrees Celsius. That is wrong. That is very wrong. What you should do is shown here in B. For the same simulation, so historical climate simulation and future climate simulation, you come to the historical period, extract a 30-year time series, for example, in the historical, go to the future and extract that same 30-year time series, say in the 2080s, and compare both. So you are comparing apples to apples. Then you will get a slightly a data change of about 3 degrees Celsius compared to 6 degrees Celsius if you compare two different data sets. Another important rule for using climate projections in practical risk assessments is respecting the integrity of modeling output. Note that climate data within an individual climate model have internal consistency. So if you are doing a climate risk assessment, for example, do not come to one model, say GCMA, take precipitation, then go to GCM, take temperature, then go to GCMB and take rainfall, put it in your climate model. If you do that and put it in your impact model, if you do that, you get a low impact. But if you went to GCMA, extracted rainfall, and then extracted temperature from the same model, put it in your impact model, the outcome will be mild impact instead of a low impact. So always respect the integrity of climate modeling outputs in your risk assessments. Note that downscale climate projections are not always better or more relevant. Downscaling will not necessarily yield more useful information to the decision maker. And increased model resolution does not guarantee superior model performance for all variables and timescales. For extreme events, final resolution, of course, is always better. There is a slight difference between a climate projection and a climate prediction. Do not confuse these two. Descriptions of future regional climate are usually referred to as projections. Projections have a range of uncertainty for a given climate variable due to differences between the results of different climate models. Also, a climate change projection is conditional on the choice of emission scenario, and this conditionality is the primary reason why a projection is not called a prediction. Typically, in a prediction, here, the phases of the observed data and the outcome of the predictive model always match each other. As seen here, you can see almost the 1:1 match here, the close correlation. But in the case of a climate model output, the projection and the historical simulation in this case and the observed data must not always match, because the climate model is initialized slightly differently using different initial conditions, so the phases must not always match with the observations. And note that a quasi resolution model might still be better than a final resolution model. So image resolution is not proportional to accuracy. Keep that in mind. Part 3. We will now look at limitations of climate modeling. Each climate model realization is an incomplete representation of reality. We do not have information about all the climate processes that occur in reality in order to represent them in climate models. So keep that in mind, that climate models are not always perfect. For example, in mountainous regions and for some processes such as convective precipitation in the tropics, it is not possible to provide reliable quantitative projections of these processes. So note that when using climate projections in risk assessments. Always keep in mind that climate models reproduce some variables better than others. For example, climate models are very good at reproducing monthly seasonal averages and reproducing large-scale weather systems compared to reproducing fine-scale systems such as convective storms. Also, in terms of variables, climate models are very good at reproducing temperature-based variables compared to precipitation-based variables, especially precipitation extremes. Climate model outputs are useful. So despite uncertainties, climate model output contributes to knowledge of plausible future change and data sets for applications such as infrastructure risk assessments. So obtained climate projection data sets, consult an expert to produce application-ready climate data and understand the limitations of climate projections before using them in climate risk assessments. Some guidance on the use of climate data sets. 1. Get baseline climate values as accurate as possible. Station data in particular is prone to a lot of inhomogeneities, differences in record lengths, and you have issues with measurement errors. So they typically need to be quality controlled before they can be used in practical climate risk assessments. Use multiple models and consider multiple emission scenarios. Understand climate data limitations and considerations before using them in practical risk assessments. Always consult a qualified, experienced climate expert in your climate risk assessment team. Document professional judgment decisions. So document what worked and what did not work when you're doing a climate risk assessment. These are important for your future reference. And that brings us to the end of this session. I would like to thank you for your time and attention today.